In October 2008, a commercial Airbus, a 330 flying from Singapore to Perth, suddenly pitched down, plunging 200 meters in 20 seconds. Passengers and crew were thrown into the ceiling as the flight computers suffered a catastrophic miscalculation. 5 years earlier, during an election in Belgium, an obscure candidate named Maria van der Vogel unexpectedly gained 4,096 votes. A manual recount of the physical magnetic cards proved her actual total was exactly 4,096 lower. And in 2013, a player speedrunning times Super Mario 64 times warped directly upward to a higher platform, a maneuver that defied the game's code and has never been successfully replicated by human input. Investigators identified these events as single-event upsets. These are hardware anomalies where a single bit of computer memory randomly flips from a 0 to a 1, independent of software bugs or human interference. Digital systems are fragile physical environments. They are constantly vulnerable to invisible forces passing through hardware, proving that information is never truly isolated from the world around it. These anomalies begin deep in space. When supernovas explode or supermassive black holes consume matter, they eject high-energy protons and atomic nuclei at nearly the speed of light. When one of these cosmic rays strikes Earth's upper atmosphere, it shatters the air molecules. This collision creates a cascading shower of subatomic particles, including neutrons, that rain down constantly onto the surface. In classical computing, memory relies on physical boundaries. A digital 1 or 0 is determined entirely by the presence or absence of electrons held inside a microscopic semiconductor well on a silicon chip. If a stray neutron from that atmospheric cascade passes through the computer and strikes the silicon in exactly the right spot, it ionizes the material. It knocks a cascade of electrons into the well, physically flipping a 0 into a 1. 2 to the power of 12 is 4,096, the exact 13th bit that flipped in Belgium. Information is a tangible entity. It requires physical space, consumes energy, and is directly manipulated by the baseline physics of the universe. If a subatomic particle has the physical properties required to rewrite our digital code, we have to consider what kind of code the particle itself is running. The physicist John Wheeler, who worked closely with Albert Einstein, proposed that every particle, force, and field ultimately emerges from fundamental yes or no questions. He called this principle it from bit. Unlike classical computers that lock bits as 0 or 1, quantum systems use qubits in superposition, holding multiple values simultaneously until they collapse. Qubits also experience entanglement. A shift in one instantly dictates the state of the other, synchronizing data across vast distances. Quantum computing utilizes nature's native logic. Every subatomic interaction, whether a photon hitting your eye or an atom emitting energy, functions as a transfer of data. At this scale, the universe operates as a quantum computer, where every collision is a literal calculation. At the Planck scale, space loses its smoothness. It ceases to be an empty container where objects simply move around, breaking down into discrete, indivisible units of information. Theoretical physicists use tensor networks to model how space-time emerges entirely from patterns of quantum entanglement. The three-dimensional geometry we move through is actively stitched together by the way these quantum bits connect and share data. This computational structure is highly visible in black holes. Rather than viewing them as cosmic vacuums that destroy everything, physicists model them as extreme quantum information processors that rapidly scramble and encode data. As this diagram illustrates, the Bekenstein bound mathematically proves that any given region of space has a strict finite limit on how much data it can hold. Crucially, that maximum limit is dictated entirely by its surface area, not its volume. This differs from simulation theory, which suggests reality is a fake construct running on an external hard drive. In this view, there is no outside system, gravity, and physics are the literal source code executing itself in real time. Gravity, electromagnetism, and the nuclear forces are the internal logic of this massive, self-executing algorithm. We observe them as fixed laws because they represent the most stable, repeatable patterns in the universe's ongoing calculation. Because we exist inside this algorithm, our ability to map it is constrained by a mathematical rule in computer science called the reflexive limitation. No machine can run a perfect one-to-one simulation of itself because the model would require more memory than the host system possesses. Trying to simulate the universe from inside the universe is like trying to fit a container inside itself. As a physical computer, the universe is bound by absolute limits on processing power, storage capacity, and energy consumption. It cannot calculate forever. The second law of thermodynamics dictates that entropy always increases. In information theory, this means usable energy is continuously converting into noise. The system is exploring more configurations over time, but it is steadily draining its capacity to perform meaningful work. Without energy gradients, the universe's calculation simply halts. Over trillions of years, as stars burn out and matter diffuses evenly, the cosmos will reach maximum entropy, a state known as the heat death. The cosmic machine will not disappear. It will remain technically active, but completely frozen. With its usable energy exhausted, the system will lack the power to process a single new event or generate any new structure. But right now, the energy is flowing and the computation is running. Human existence is a temporary, highly complex output of this finite calculation. We exist in a brief window where the algorithm evolved enough to look up, track the flow of information, and study its own source code.